Very good morning to everyone, and I welcome to today's one hour lecture on power management technique in embedded system. So this is my seventh lecture in this series. So as embedded system continues to become smaller, then smarter and more pervasive, from wearable devices and IoT nodes to automotive and industrial controllers, efficient power management has become a critical design requirement rather than an operational feature. The performance, reliability, battery life, and overall sustainability of an embedded product are all directly influenced by how effectively power is managed. In this lecture, we will take a concise yet comprehensive look at the fundamentals of power management in embedded systems. We will begin by understanding why power efficiency is so important and identify the primary sources of power consumption within embedded hardware and software. From there, we will explore a range of power reduction techniques, including both hardware-based approaches such as low power components and power modes, and software-based strategies like task scheduling, then sleep states, and the dynamic power control. We will also discuss in this session the key challenges or key design consideration for selecting the appropriate power management strategies based on applications requirements, operating conditions, and system constraints. By end of this session, we will have a strong foundational understanding of power management principles and how they are applied in practical embedded system designs. So coming to the first slide, the title of this topic is Introduction, the importance of power management. In embedded systems are everywhere in our daily lives, often working silently in the background. They range from small battery powered devices such as smartwatches, then fitness trackers and wireless sensors to large grid connected systems used in industrial automation, then medical equipment, then automotive electronics and communication infrastructure. Despite their wide variety of applications, on one common and critical design concern units all embedded system, that is power management. So power management actually plays a vital or a very significant role because it directly affects how the efficiently and reliably an embedded system operates. Let us first consider a battery life, which is especially important for portable and wearable devices. Generally, users expect a longer usage time and fewer charging cycles. So, effective power management technique can significantly extend the battery life, improving user experiences and product competitiveness. The next is heat dissipation. So high power consumption actually leads to increased heat generation within electronic components. So excessive heat can degrade the performance, then reduce the reliability and even cause permanent damage of the devices. So managing power efficiently helps keep operating temperature low and avoids the need for bulky or expensive cooling solution like heat sink or any external cooler. Now, energy efficiency is another major factor. Even if the system is connected to a constant power source, reducing the energy consumption lowers the operating cost and supports the environmental sustainability. In addition, the system cost can be reduced through smaller power supplies and simpler thermal management. So finally, lower power consumption or lower power operation enhances the reliability as component operate at very low temperatures generally last longer. So for this reason, power management is a very important and very fundamental consideration in embedded system design. Now coming to the next slide, here I am going to discuss the what are the types of power what are the types of power sources are available in the market. The title of this slide is sources of power consumption. Now to design an energy efficient embedded system, the first and most important step is to clearly understand where and how power is being consumed. So power consumption in embedded systems does not come from a single source. Instead, it is distributed across several components and operating activities within the system. Let us now examine the primary source of power consumption in detail. The first one is known as, it is very popular power consumption mechanism, which is known as dynamic power consumption. So the dynamic power is basically is the power consumed due to the switching activity in digital circuits. So every time a transistor changes its states from logic 0 to logic 1 or vice versa, it charges and discharges a capacitance. For example, like CMOS inverter. In CMOS inverter, when the input voltage is 0 and the output, when the input voltage is 0, the output voltage becomes high, and at the output terminal there was a one load capacitor, and that particular capacitor basically used for charging and discharging operation. So this is one real-time example. So in CMOS logic, this charging we can easily observe the dynamic behavior or dynamic power consumption in switching mechanism. This is one kind of switching mechanism. So this switching activity consumes the energy, and the total dynamic power is approximately given by the equation, that is E equal to C stands for the load capacitance, and V is the power supply voltage, and F stands for the frequency, in which particular frequency the input voltage is changing from one state to another state. So here just now I told C represents the effective capacitance, and V is the supply voltage, and F is the switching frequency. So from this relationship we can clearly see that the reducing voltage or operating frequency can significantly lower the dynamic power consumption. because the power is proportional with respect to power supply voltage as well as frequency. Now coming to the next important power consumption technique, that is known as static power consumption. So what is static power consumption? Static power, also known as leakage power. So this power is consumed even when the circuit is in ideal or non-switching is taking place. Means it is on ideal state whenever we are not using that particular circuit, like CMOS inverter. We are not applying any voltage at the input terminal. On that time also there will be a leakage power consumption due to the flow of leakage current. So it is mainly arise due to the leakage current in the transistor. So as modern semiconductor technology moves towards smaller transistor size, then leakage current increases, making static power a major concern, especially in low power and always on devices. Another contributor is short circuit power, which occurs during brief transition when both NMOS and PMOS transistor in CMOS get conducted simultaneously, although this happens for a very short duration, and frequent switching can make this component noticeable. So in addition to the processor core or peripherals devices such as sensors, displays, communication module, and interfaces can consume a significant amount of power, often dominating the total system consumption. The memory component, including RAM and flash, also contribute to power usage during read, write, and refreshment operations. So finally, the clock tree, which distributes the clock signal across the chip, can consume a substantial portion of total power due to its continuous switching activity. Understanding these sources is essential for effective power management and optimization. Now, coming to the next slide, that is hardware power management techniques. So once we understand where power is being consumed in an embedded system, the next step is to explore hardware level techniques that can effectively reduce the consumption, reduce this consumption. So hardware power management plays a very crucial role because many power savings can be achieved directly at the circuit and architectural level, often without impacting the system functionality. So one of the most widely used technique is dynamic voltage and frequency scaling. So it is very popular, and the commonly it is known as DVFS. So in this approach, the processor operating voltage and the clock frequency are dynamically adjusted based on the current workload. So when the system is executing the computational intensive task, the high voltage and the frequency are used to meet the performance requirements. However, during the ideal periods or less demanding operation, both voltage and frequency can be reduced. Since the dynamic power is proportional to the square of the voltage, as I already mentioned in the previous slide, C equal to P power, dynamic power is equal to C into VDD square into frequency. So since the dynamic power is the proportional to the square of the voltage, Even a small reduction in voltage can lead to significant power of savings. Why? Because VDD square. So if the voltage is 5 voltage, if the power supply voltage is 5 millivolt square, means 25 millivolt. If we will reduce 5 to 4, then the what will be the effective voltage? That will be uh, uh, 4 square means 16 millivolt. So previously it was 25 millivolt, but if we change only a small amount of voltage, 1 volt, if we change from 5 voltage to 4 voltage, then you can see the effective voltage will be reduced approximately 9 millivolt, because when we will take the power of 4 is the VDD is 4, that means VDD square is 16. In the previous day it was 25, so square of 5 means 25, means we able to reduce the voltage from uh, 25 to 16, means 9 millivolt we are able to reduce. If it is 3 volt, then the overall voltage will be 9 volt. So effectively how much voltage we can reduce? 25 minus 9 means approximately 16 volt, 16 millivolt we can able to reduce. That is the biggest advantage. We'll able to reduce very small or significant amount of voltage, which can lead to the significant amount of power savings. Another important technique is called clock gating. So here the clock signal is selectively disabled for modules that are not currently in use, because the clock signal causes frequent switching. Then stopping the clock prevents unnecessary transition and reduces the dynamic power consumption. So clock gating can be applied at different levels, ranging from individual registers to entire functional blocks. So power gating goes a step further by completely shutting off the power supply to inactive modules. So this technique eliminates both dynamic and static or leakage power. While the power gating offers substantial savings, it introduces wake up latency when the module needs to be turned back on, which must be carefully managed in time critical systems. In a multi-voltage design, different blocks within the same system operate at different voltage level. So the performance critical components run at higher voltages, while non-critical or background modules operates at lower voltages, reducing overall power consumptions. So using low power memory technologies also contributes the significantly low power reduction. Uh, the techniques such as reduces the refresh rate, then sleep mode, and power down states help to minimize the memory related energy consumption. Then adaptive body biasing is another advanced technique where the body voltage of the transistor is adjusted to control the leakage current. So reverse body biasing reduces the leakage power, while forward body biasing can temporarily improve the device performance. So finally, specialized hardware accelerator can be used to offload the specific tasks such as signal processing or encryption. So this accelerator performs the dedicated functions more efficiently than general purpose processor, resulting in lower energy consumption per operation. Together, these harder techniques form the foundation of effective power hour embedded system design. Now coming to the next slide, here I will cover the software power management. So in addition to hardware level strategies, the software plays a an equal critical role in managing power consumption in embedded systems. So software has a direct control over how hardware resources are used, when they are activated, and how efficiently computations are performed. By making intelligent software level decision, the significant power savings can be achieved without changing the underlying hardware. So one of the most important approaches is the use of power aware operating system. In modern real-time operating system, or RTOS, often include built-in power management features. So this system can intelligently schedule the task to minimize the unnecessary switching activities, manages the idle time efficiently, and control the power states of various hardware components such as CPUs, memory, and peripherals. By coordinating system activities, the RTOS actually ensures that hardware is only active when it is required. Then sleep modes are another fundamental software controlled power saving technique. When the system or specific peripherals are ideal, so software can place them into low power sleep states. So the different sleep modes provides the different trade-off between the power savings and wake up latency. Shallow, the sleep modes allow quick wake up with the moderate power savings, while deeper sleep mode offer maximum power reduction at the cost of longer wake up time. Now, the efficient interrupt handling is also an essential. Poorly designed interrupt service routine can keep the processor active for longer than necessary. So by minimizing the interrupt latency, reducing the number of interrupts, and designing short and efficient interrupt service routine, that is called ISR, the processor can run to low power states and more quickly. Then another software power management technique is algorithm optimization, further contributes to power efficiency. So selecting algorithms and data structure that require fewer computation, which reduces the total number of operations executed, which directly lowers the dynamic power consumption. So that means software is also directly interrelated with power consumption. So lengthy algorithm is will take more. It will take more. The computation complex algorithm needs more computation. So more computation means it required more energy. So more energy means the power consumption will be more. So it is directly interrelated with software power management. Similarly, the code optimization. Just now I told the optimization technique also one important thing, such as compiler optimization, then loop unrolling, and the eliminating redundant instructions, which helps to reduce the execution time and energy usage. And the effective peripheral management involves turning off or scaling down unused uh, peripherals through the software control. Finally, the dynamic task scheduling allows to task to be grouped based on the shared resources usage, reducing the frequent power up and power down cycles. Together, these software techniques form a powerful toolkit for achieving energy efficient embedded system design. Now coming to the next slide, the power management strategies and consideration. So selecting an effective power management strategy is a critical steps in embedded system design, and it must always be guided by the specific requirements of the target application. There is no single solution that fits all systems. Instead, the designers must carefully evaluate multiple factors to achieve an optimal balance between performance, power consumption, cost, and reliability. The first and most important factor is application requirements. So every application has unique performance demands. The battery life, expectation, and operating conditions. For example, a wearable health monitor prioritizes ultra-low power consumption and long battery life, while an industrial controller may prioritize performance and reliability over energy savings. Environmental conditions such as temperature, humidity, and duty cycle also influence the choice of power management techniques. Understanding these requirements early helps narrow down the suitable strategies. The next system architecture plays a major role. Uh, the choice of the processor, memory types, peripherals, and interconnects directly affects which power management options are available. In some processors support advanced features such as multiple sleep states, then dynamic voltage and frequency scaling or power gating, while other do not support. Similarly, in the presence of power hungry peripherals or external components can significantly influence overall power consumption. A well-planned architecture enables more flexible and effective power control. Another key consideration is the power budget. Uh, Establishing a clear power budget early in the design phase provides a quantitative target for the entire system. So this budget defines how much power each subsystem is allowed to consume and helps designer make informed trade-offs. Without a well-defined power budget, power management decision often becomes reactive rather than systematic, leading to inefficiencies later in the design process. For systems with timing requirements, real-time constraint must be carefully evaluated. In real-time embedded systems, tasks must meet the strict deadlines, while the low-power modes can significantly reduce the energy consumption. They also introduce wake-up latency. So designer must ensure that the system can transition from low power state to active mode quickly enough to meet the real-time deadline. This often requires a careful balance between the power savings and responsiveness. So complexity and cost are also important factor. In advanced power management techniques such as multi voltage domains or the aggressive power getting can offer substantially energy savings, but they also increased the design complexity, verification effort, and the hardware cost. In cost sensitive applications, simpler techniques may be preferred even if they provide slightly low power savings. So power management inherently involves trade-offs. Reducing power consumption often impacts the performance and improve performance, typically increasing the energy usage. For instance, the aggressive DVFS can lower the power consumption during low workloads but may reduce performance during peak demand. So designer must carefully evaluate these trade-offs to meet the system level goal. So finally, profiling and measurement are essential for effective power management. The accurate power profiling helps to identify the power hotspot and validate the design assumptions. So tools such as power analyzer, simulator, and emulator enable designers to measure the real world power consumption and assess the effectiveness of implemented techniques. In summary, I can say that the successful power management requires a holistic approach that considers applications needs, system architecture, then timing constraint, then cost and measurable data to make informed design decision. Coming to the next slide, it is future strategies of power management in embedded systems. As embedded system continues to evolve, power management has become more intelligent, adaptive, and system aware. Future embedded devices, especially those used in mainly in AI, IoT in healthcare or automotive and wearable applications, will demand ultra low power consumption without compromising the performance. So to achieve this target, several advanced power management strategies are emerging, like AI-driven power management. Here, one of the most promising future strategies is used of artificial intelligence and machine learning for power consumption instead of relying on fixed rules. AI-based system can learn usage pattern, predict the workload, and dynamically adjust the voltage, frequency, and power states in real time. So this allows smarter decisions that balance performance and energy efficiency more effectively than traditional methods. The second important power management, another strategy is context aware power management. So future embedded system will become context aware, meaning they will adjust power consumption based on environmental condition, user behavior, and operational context. For example, sensor may reduce sampling rates when no significant changes are detected, or system may enter deeper sleep modes based on the location, time, or activity patterns. Number three, that is ultra low power and near threshold computing. So operating a processor at near threshold or subthreshold voltage is an important future direction. While this reduces power consumption drastically, it introduces challenges related to the performance and reliability. So ongoing research focuses on making near threshold computing practical for real world embedded applications. Coming to the point number four, that is advanced power gating and fine uh, grained control. So future system will implement fine grained power gating where individual functional blocks, cores, or even submodules can be powered or on or off independently. So this granular control may minimize the leakage power and enables the aggressive energy savings, especially in multi-core and heterogeneous architecture. Then the fifth one is energy harvesting integration. So energy harvesting using solar, thermal, vibration, or RF synergy will play a significant role in future embedded systems. So power management strategies will evolve to adapt dynamic to intermittent and unpredictable energy sources, enabling batteryless or energy neutral operations in many applications. Number six, that is called another strategy is future strategy heterogeneous accelerator centric design. So future embedded platform will increase rely on the specialized hardware accelerator for tasks such as AI inference or signal processing and encryption. So power management strategies will focus on intelligently offloading tasks to the most energy efficient hardware blocks rather than the general purpose CPU. Next one is software defined power management. So power management will become more software defined, allowing updates and optimization through the firmware rather than the hardware redesign. This flexibility enables long-term energy optimization even after the deployment. And the last one is cross-layer power optimization. So the future strategy will emphasize cross-layer optimization where power management decision are coordinated across the hardware, operating system, then middleware and application. So this holistic approach ensures the maximum efficiency at the system level rather than the isolated component level. Now, in conclusion, the power management is one of the most crucial and challenging aspect of modern embedded system design, especially as device becomes smaller, smarter, and more energy constrained. And effective power management approaches beings with a clear understanding of the various sources of the power consumption within an embedded system, including processing unit, memory, peripherals, and communication interfaces. By accurately identifying these power-hungry components, designer can make informed decision about whether but the optimization efforts will have the greatest impact. So the use of this well-designed hardware techniques such as dynamic voltage and frequency scaling, clock gating or power gating, and low power memory technologies combined with software level strategies including power aware operating system, sleep modes, efficient interrupt handling, and optimized algorithm enables significant reduction in overall energy consumption. So this technique not only help extend battery life in portable and IoT devices, but also reduce the heat generation, enhance the system reliability, and lower overall system cost. And equally important is the carefully evaluation of the application requirements, system architecture, and power budget during the early stage of design. So power management is not a one-time task, but a continuous process that requires regular monitoring, then profiling and optimization throughout the system life cycle. By adopting a holistic and proactive power efficient while maintaining the desired performance and the functionality of the embedded systems. So thank you one and all.